Hello everyone, welcome to week 2 live session of NPTEL's Introduction to Semiconductor Devices. I am Om and today we will be solving some questions that will help you with your assignments. So let us start. So in this week, uh, we will be looking at carrier properties, intrinsic carrier density, Fermi level, donor and support impurities. So mainly we'll look at intrinsic carriers and Fermi level and we'll solve some questions based on it that will help you with your exams. In case you have any doubts anywhere, please feel free to uh, raise your hand or you can unmute and ask the questions or you can type in the chat as well and monitor them. I'm audible, right? Am I audible?
Yes, sir.
Okay, thank you. So let us start. We start with some simple questions. The first question is we have to choose the correct statement. In a doped semiconductor, the ionized dopants can move freely in the lattice. And the second is in the doped semiconductor, the ionized dopants do not directly contribute to the current flow. So we have to tell which of these is the correct. Okay, so Mikala says second is correct. Anybody else? Okay, so second is correct. That's true. Uh, Lakshay is saying both one and two are correct. No, one is incorrect because you see when we have a semiconductor, right? Uh, it's a silicon. It's a doped semiconductor. So you dope it with let's say N type. That means group 5 impurities. Could be let's say phosphorus. So phosphorus would have 5 electrons. It will give one electron away and become positively charged. There will be these will be the donor atoms. And these will be the electrons given by it, and these are the donor atoms. So when you apply electric field or try to flow the current, these electrons will move. These donor atoms will remain fixed at their place. So donor atoms cannot move freely. This is incorrect. And as a result, they do not directly contribute to the current flow as they do not move. These donor atoms do not move. The electrons given by them, they move and contribute to the current. Is this clear? Why the first one is incorrect? Okay, great. So let's move on to the next one then. Please read this question and try to solve it. So the question says the electron concentration in a piece of silicon maintained at 300 Kelvin under equilibrium is 10 to the power 5 per centimeter cube. The whole concentration is what? The intrinsic carrier concentration is 10 to the power 10 per centimeter cube. Right, it is A. So we will use the law of mass action, which is NP equals to Ni square, which is true for universally for the non-degenerate semiconductors. So when Np equals to Ni square, here we know electron concentration is given. N is 10 to the power 5, Ni is per centimeter cube, Ni is 10 to the power 10 per centimeter cube, and P is Ni square. So 10 to the power 5 into P, 10 to the power 10 square. P is 10 to the power 20 by 10 to the power 5, which is 10 to the power 15 per centimeter cube. Is option A. Any doubts in this part? Okay, if not, so let's move on to the next one. Okay, please read this question and try to understand what it's being asked. Okay, so let's look at this question. What it says is a particular intrinsic semiconductor has a resistivity of 100 ohm per centimeter at T equals to 300 Kelvin and 10 ohm per centimeter T equals to 330 Kelvin. So we know rho 1 is 100 ohm centimeter at T1 is 300 Kelvin, rho 2 is 10 ohm centimeter at T2 is 330 Kelvin. If the mobility of the carriers and the energy band gap remain unchanged with temperature, the band gap of the semiconductor is. So we have to find out the band gap of the semiconductor, and a hint is given. Ni is T to power 3 by 2 exponential minus Eg by 2 kT. Okay, so we know that the conductivity sigma equals to Nq mu, or I can write it as 1 by rho is, or for intrinsic it will be Ni Q mu. So we can write rho 1 by rho 2 equals to Ni2 by Ni1, right? Rho 1 equals to Ni1 Q mu, 1 by rho 2 equals to Ni2 Q mu. Q is constant and mobility also is also constant as given in the question. So rho 1 by rho 2 is Ni2 by Ni1, and using this relation, we will replace this T2 to the power 3 by 2 exponential minus Eg by 2k T2 upon T1 to the power 3 by 2 exponential minus Eg by 2k T1 rho 1 by rho 2. Now if I just try to rearrange this and solve this further, rho 1 by rho 2 is T2 by T1 to the power 3 by 2 exponential of Eg by 2k 1 by T1 minus 1 by T2. Substituting all the values, 100 by 10 is 330 by 300. Eg we have to find 2k 1 by 300 minus 1 by 330. Now, okay, so this 10 is 11 by 10 to the power 3 by 2, Eg by 2k 30 upon 300 into 330. And we know this kt, k into 300 is 0.026. Right? So I can replace this. 10 is, I'll solve this value as well. 1.1536 exponential Eg 8.4965 by 2. Okay, now I substitute to find Eg. So Eg will be ln 10 by 1.1536, 2 by 3.4965. So this whole value is 3.4965 and this value is 1.1536. So on solving this, we got 0.235 electron volt. which is option B. Okay, so calculation has bit involvement, but question is easy. Is this clear to all? Any doubts in this part? Okay, so I'll explain it again. The question says we have an intrinsic semiconductor that has resistivity of 100 at this temperature and resistivity of 10 at another temperature. We have to find the band gap Eg for the same semiconductor, and the conditions are given that the mobility and the band gap are constant with temperature. So this is the question. So given this and this, we have to find Eg. And we already know that the conductivity sigma is and q mu for intrinsic n will be ni. So we just take the ratio of rho 1 by rho 2. It should be ni2 by ni1. And we substitute this expression for both of these ni2 and ni1. Any other doubt in this? Yes, intrinsic carrier concentration is changing. Yes. Yeah, that happens. This relation is given, right? This is correct. Any other doubt? So Ni does change with temperature. So Okay, if not, let's move on to the next one then. So why Ni changes with temperature? Because Ni is just these are the intrinsic carriers, and where intrinsic carriers are coming from the thermal generation and recombination, right? So if you increase the temperature, the rate of thermal generation recombination will increase. So your Ni will increase. Okay, next question. Okay, so let's see this. Consider a silicon dope with boron. So this is p-type dope. Concentration of this Ni is this, and Vt and temperature are given. Compared to undoped silicon, the Fermi level of the doped silicon is what? So we have Ec, Ev, Ei, and once since we have doped with boron, we will have Ef somewhere here. So in p-type doping, Ef will be closer to Ev, right? And in n-type, the opposite. Ef will be closer to Ec. Okay, so we can find this Ei minus Ef. This Ei minus Ef is given as Kt ln Na by Ni. Na is the doping. Na is 4 into 10 to the power 15 per centimeter cube. Ni is 1.5 into 10 to the power 10. And this Kt is nothing but Vt, which is 0. 0.026 electron volt. So EI minus EF will be 0.026 ln N is 4 into 10 to the power 15 by 1.5 into 10 to the power 10. Okay, so now if we solve this, we will get EI minus EF is 0.32, almost equal to 325 electron volts. So this value is 0.325 electron volt. So answer will be option C. EF shifts from EI to EF towards EV, right? Shifts by 0.325 electron volts towards EV. Okay, so any doubts in this question? Okay, let's move on to the next one then. Question 5 is find the correct plot that depicts the position of Fermi level corresponding to non-degenerate doping for N-type and P-type material. Try to solve this. Okay, Michaela says D. Anybody else has any other answer? We all think it's D. Okay, so D is incorrect. D is not correct. Can you take another guess? So okay. So tell me, for N-type dope, EF is closer to where? And for P-type, EF is closer to where? Is it EC or EV? Right. It's EC and EV. So, so here what is happening if you see, you are increasing the doping concentration from 10 to the power 12 to 10 to the power 18 in both N-type and P-type. So the EC would go, this Fermi level would go closer to, would go closer and closer to EC, right? So the answer is this option A. Michaela, why slope is not possible? Can you please explain what is non-degenerate semiconductor? So non-degenerate just means it is low dope, right? The doping is not very high, which is like EC minus EI is always greater than P, or EI minus EF is always greater than EC minus EF, or EF minus EV is always greater than P. This is the condition for non-degenerate doping. It has nothing to do with slope. So when you are increasing the doping concentration, so definitely there will be slope, right? Where there is low end doping, then this EF minus EI will be higher. And here doping is high, so EF minus EI, EF minus EC is, sorry, EC minus EF is lower. Since you are increasing doping, EF will move closer to EC. Similarly here, when you are increasing doping, in the P-type, your EF will move closer to EV. So option A is correct. Is there still any doubt in this? Should we move on to the next one? Okay, so let's take the next question then. Okay. Correct statement regarding the mobility of carriers in semiconductor. Okay, the first part is the unit of mobility is centimeter square per second. Second is higher lattice force experienced by holes mu p per semiconductor material surface mobility is smaller than the bulk. The last part is mobility depends on temperature. So, which of these is incorrect? A is correct. A, the unit of mobility is centimeter square per volt second. This is correct. So the wrong one is among these three. Which one is incorrect? Okay, so since you're stuck in this, let me answer it. This is also correct. This is also correct. So mobility actually changes with temperature. It first increases in general cases. So mobility changes on depends on temperature. This is correct. For semiconductor material, surface mobility is smaller than the bulk. This is also true because in a semiconductor, where we have some interface, let's say oxide and silicon, so the mobility here will be higher compared to mobility here because due to some impurities here and the different dangling bonds, the mobility actually reduces at the surface. The new surface is less than mu bulk, which is always true. And the unit of mobility is centimeters per volt second. This is also correct. The only incorrect one is this one. This is incorrect. So answer is option B. So why this is incorrect? Because we know mu n is always greater than mu p. Why this happens? Because if you remember the energy bands, band structure looks something like this. EC, this is EV. So the curvature of EV is greater than EC, and the effective mass of force therefore is much is greater than the effective mass of electrons. And mobility is directly depend on that. Therefore, this happens. So option B is the right answer. Yeah, conventionally the unit is centimeter square per volt second. That's what it is given right here. Centimeter square per volt second. This per, right? This is I think not visible clearly, but slash here. Are there other options clear? Why this one is incorrect and why these are correct? The standard unit. So in standard terms, you would just change this to meter square, right? But you see the overall, this is like some distance square. This is the volt and this second. This will not change. It can be centimeter or meter, does not matter. But yeah, overall, this is the unit. which describes mobility. This is not an incorrect unit. So you can also see here the drift velocity VD is by inches. VD can be centimeter per second. The speed electric field will be watt per centimeter, centimeter square per volt second. Is this clear? Okay, so let's take the next one. See this one first. A piece of silicon is doped uniformly with phosphorus n-type doping with a doping concentration of 10 to the power 16 per centimeter cube. This is ND. That's the value of mobility versus concentration for silicon as a full dopant ionization is shown below. So mobility versus doping concentration is given the plot. The charge of an electron is this, the conductivity in Siemens per centimeter cube of the silicon sample at 300 Kelvin. So we have to find sigma. ND is 10 to the power 16 per centimeter cube. Temperature is 300. Okay, so how do we solve this? Okay, so let's solve this. We know sigma equals to NQ plus P2 P. But since we are talking about the n type, let us ignore this. We can ignore the 6. P is not P is less than n. So we can ignore this. So sigma is NQ and we know exactly 1.3 10 to the power 16. 2 is 1.6 into 10 to the power minus 19. What is mu n? Mu n we can see that is 10 to the power 15, this is 10 to the power 17. Here at 10 to the power 16, mu n is 1200 centimeters square per volt second, right? So you have to find it from this graph. So mu n will be 1200. So when we solve this, what we get is 1.251 per centimeter square. Is option C. Please go through it again and let me know if you have any. Okay, any doubts in this? Next question. The donor concentration in a sample of silicon is increased by a factor of assuming the sample to be non-degenerate. The shift in Fermi level is what question says. ND1 is it's a ND, ND2 is 100 times ND. And so EI, this is EF1, EF2. We have to find this EF2 minus EF1 is the question. Let's try this out. So how do we solve this? Is we know Px minus Pi is KTL. So Pf1 minus Pi KT and 1 by Pf2 minus Pi is KT. Let's subtract 2 minus 1. We will get Pf2 minus Pf1 is KT ln and d1 by 7 to d2 by 7 d1 by 9, which is KT ln and 2 by ND1, just KT is given 0.025 ln ND2 by ND1 is 2. So to solve this, we get 0.115 electron. Any doubts in this question? Okay, next question. For a non-degeneratively doped n-type silicon, which of the following plots represents the temperature dependence of free electron concentration? Okay, so let's think about this one. So let us try to draw n versus temperature T first. Then we'll figure out the next part. So we know if I try to draw Ni versus temperature, it is Ni proportional to something like exponential kind of relationship, P by 2 exponential Cg by Kt, something like this. So Ni will exponentially increase with temperature. Ni. Now I want to draw N. So how N will behave is something like this. Increase, saturate, and then increase again. So now this is called freeze out zone. This is called extrinsic. Where is equal to 3. This is the intrinsic zone. So what happens is when you're starting, let's say at very low temperature, the thermal energy is slowly increases, which gives sufficient energy for the donor atoms to donate one electron. So slowly here, as temperature increases, more and more donors are giving the electron. Here, after a certain temperature, all the donors have ionized. Then the doping is constant at ND here. Then when you further increase the temperature, what happens is this thermally generated carriers become more than Ni becomes more than ND. So Ni becomes more than ND. So N becomes equal to Ni here, N equals to ND. So overall, what happens is the electron concentration first increases, then remains constant, and then increases again with temperature. Right? So this is the overall understanding. Now the question is we have to draw log n versus 1 by t. So If something is increasing with temperature, it will decrease with 1 by T, right? So a plot will become something like decreasing, then constant, and decreasing again. This region is high temperature, this low temperature, right? So the answer will be option A. Is this clear? Any doubts in this? Okay. If not, I think I have one more question. Let's try to solve this. Right. It is both ME and MH. And the relation is given as EA minus EE is 3 by 4 KT ln MH upon M. So your intensity, your Fermi level depends on both MH and E. Okay, so these were all the questions for today. If you have any doubts, please feel free to ask, else we can close the session.
I yeah, just one point to ask.
Yes.
Which book do you suggest to have concepts of these questions?
Okay.
Any reference book?
Yeah. Understand. I think the reference books are suggesting in the course. Yeah.
I actually started with book called Pirate, and this is too mathematical. relatively easier book. Yeah. Yeah, the first one I started with
Okay,
is too mathematical.
so you can
I
start
think
with
this
maybe
name,
this book,
right? I think
Smith.
name. Okay,
So this is a
Cedrat
relatively,
Smith. Okay.
yeah, it is relatively easier,
Mhm.
but yeah, it is like very high level. So if you want to know something more about it, you should go to the period book.
All right. All right. Okay. I'll do that.
Okay. Anything else? Okay, then thank you all. Thank you for joining. We will see you next week.
Yeah, will this video be available
Yeah, I
after this
am.
class?
Yeah, I am uploading the videos uh, in the link in the problem solving section. Are you not able to see it?
That link I could not get. The previous lecture I was trying to
Okay, I'll share it with
see
you.
again.
Just a minute.
Yeah, yeah, please.
Are you able to open this? See.
Yes, 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 got it. Got it. I'll say thank you.
Okay, so you can bookmark this and all the
Yeah,
lecture notes as well as the YouTube videos from all the three TAs will be available after each section in this link.
all right.
Okay, okay. Thank you for joining. Bye.
Yeah, thank you.